So in the last lecture of this course, we will look at the celebrated question about P and NP, which is often mentioned as one of the last and most important open problems in computer science. So we have seen that a checking algorithm is something which allows us to verify whether or not a given problem's solution is valid. So a checking algorithm doesn't necessarily solve the problem itself, but what it can do is take an input to the problem, a potential solution to that problem, and validate whether or not that solution is indeed one. Right? So without having to solve the problem itself, it can just check whether a given solution is a valid solution or not. So the class NP is the class of problems for which such checking algorithms exist, with the additional constraint that the check runs in polynomial time in the size of the input. Right? So the checking should be efficient. So in all the problems we have seen in the last lecture, this is in fact true. Factorization is an NP because given two factors we can multiply them efficiently to get the answer that we want and check. Satisfiability again because we just have to take the assignment of true false to the formula variables and verify whether the formula evaluates to true after that. Again, traveling salesman, the bounded version, we can take a set of a given path, check it as a simple cycle, add up the weights and verify that the bound is satisfied. Likewise, vertex cover and independent set, right? So these are all in NP because the solution can be validated efficiently with respect to the input size. One thing to note is that in problems like traveling salesman, vertex cover and independent set, we took an optimization problem and converted it into a bounded checking problem. But we also said that the bound could then be exercised using binary search in order to find the actual answer. So this binary search adds a logarithmic factor. So overall, in some sense, there is no loss of generality because you take a polynomial times step and then you multiply it by a logarithmic thing, so everything is still the same. So there is no difference really between the pure checking problems like satisfiability and the modified checking problems which involve introducing a bound like traveling salesman or vertex cover. So why is this class called NP? So NP comes from the word non-deterministic polynomial time. Right? So this is a historical reference. So it refers to the fact that these correspond to problems where you can non-deterministically guess a solution. Right? You can magically produce a solution and then in polynomial time you can verify whether the solution is correct or not. So the actual origin of this term comes from computability theory, from the theory of non-deterministic Turing machines. So if you have studied that, then you will know why it is called NP. But if you have not studied that, it's not so important as to realize what it implies for algorithms. So NP comes from non-deterministic polynomial time, which in turn comes from Turing machines. So the two classes that people talk about are P and NP. So we have just seen what NP is. So what is P? So P is just a class of problems which we have been trying to explore in this course. These are problems for which you have a worst case algorithm which runs in polynomial time. Right? So recall that we said right at the beginning that we are looking at problems of the form n squared, n cubed and all that. We are probably looking at even less in terms of practical things, such things like n log n, but we certainly don't want 2 to the n and n factorial. Right? So P is the class of all problems, a regular polynomial time complexity in terms of worst case. Now by our definition, everything in P is also an NP because we don't need to get a solution to check it. Because it's in P, we can actually generate the solution ourselves. Right? So a checking algorithm asks somebody to give us an input and a proposed solution and then validate it. A problem in P, we can actually generate the solution so we can validate it again. And therefore every problem in P is actually an NP. So the question that people want to know is whether P is equal to NP. So it's a converse true. Is it possible that whenever I have an efficient checking algorithm, I also have an efficient algorithm to generate a solution? So intuitively, this does not seem to be the case. As we observed, the teacher who is checking the factorization homework need not even know how to factorize. The teacher only needs to know how to multiply. Right? So it seems intuitively much simpler to check a solution than to actually generate one. So let's see whether this intuition can be made formal. Right? So why do people believe that P is not equal to NP? Well, one of the reasons is just from experience or it's empirical. So we have seen many natural problems, factorization, satisfiability, traveling salesman, vertex cover, independent set. These are all in NP. We have seen that vertex cover and independent set can be reduced to each other. Today we will see that some other NP problems can also be reduced to each other. Okay? So in fact, you can find that all these problems actually are inter-reducible. This means that they effectively have the same level of hardness, because when things are reduced between one and another, either you can transport efficient solutions or you can claim inefficiency. But effectively, they're all of the same type. If you can solve one, you can solve the other in roughly the same amount of time. So all it takes to solve any one of these, and all of these problems will then have an efficient solution. But people have been trying these problems from different angles for many years now, and nobody has found one. Therefore, there is good experimental evidence that there is no good solution for these. So let's look at these inter-reducibilities a little more closely. So we start with Boolean satisfiability. Recall that in Boolean satisfiability, we have clauses. Clauses are composed by disjunction of literals. So we take X or not Y or Z or blah, blah, blah. Right? So we have these ors strung together to form a clause, and then we put these clauses together with an AND. So in general, we argued that it is hard to think of how to find a satisfying assignment, but if we get an assignment of values for all the variables, we can quickly check whether it makes it true or not. So a restricted form of satisfiability is called 3-sat. Right? In 3-sat, we have only clauses like X or not Y or Z. Okay? Or we could have two also, X or Y and so on. So we could have even trivial things like Z, but remember, if I have a clause which says Z, the only way to make it, this forces me to make Z true, because there's no option. If I have X or Y, I can make X true or Y true. So a clause like this doesn't contribute much to my problem, because it forces a valuation for a particular variable, and then I can reduce the problem to one which has 2 or 3. So 3-sat has typically 2 variables or 3 variables, but not more than 3. It doesn't have 4 or 5 variables. So the first claim is that 3-sat is as general as sat. So we'll show this just by a simple example. So supposing I have a given clause which has 5 variables like this. Okay. So what I want to do is I want to have only 3 variables. So what I will do is slice off this part. So I will keep the first 2 and I will slice off this part. So I will introduce a new variable A, and I will say it is V or not W or A, and I will put a not A with the rest. Okay. So now what does this tell me? So this tells me that supposing in this case that these are both false. Okay, then in order to make this true, I must make A true. But if A is true, then this is false on the other side. So that means that if this clause is true, one of these is true. So in other words, it's saying if both V and not W are false, then one of the other 3 variables must be true, which is exactly what the original clause is saying, that one of these 5 must be true. Okay. On the other hand, if V or not W is true, then I can afford to set A false. If A is false, not A will become true, then I have no obligation on the remaining variables. Right? So the claim is that by this expansion, okay, by removing this one, by splitting away the first 2 variables and adding this intermediate thing linking the 2 clauses, I produce 2 clauses which have the same satisfiability as the original clause. Now again I have, unfortunately, too many variables here. So what I will do is I will now again keep 2 and split the rest off. Right? So I'll keep not A X, and I'll introduce new variable B, and then I will take not B and take the remaining 2. Okay. At this point, fortunately, I have now reduced everything to 3 variables. I can stop. If I had 4 variables still, again I will do the same thing. I'll do C and not C and so on. Okay. So in this way, I can take any clause which has more than 3 literals and systematically decompose it by adding new literals into a sequence of 3 literal clauses. So I can convert any clause which is not in 3-sat into a sequence of 3-sat clauses. And how big is the sequence? Well, it's going to be proportional to the number of literals in the clause. So the blow up in my formula is going to be linear in the original formula. That's important, because we said that when we do reductions, right, we want the reduction part to be efficient, to say that we are not spending so much time on the reduction, otherwise we can't transfer efficiency claims across. So what this tells us is that if SAT is hard, as we believe, then so is 3-sat. Okay, because I have reduced SAT to 3-sat. So far we have seen reductions which are not very perhaps surprising. We have seen independent set, okay, and vertex cover. But these are similar problems. Similarly, we have seen SAT and 3 SAT. Okay, these are similar problems. Now what we're going to do is we're going to bridge the gap between these two different problems. We're going to look at 3 SAT and say that 3 SAT actually can reduce to independent set. Okay, which is a little bit more surprising because they seem to come from very different domains. So here is a typical 3 SAT formula. So we have 1, 2, 3, 4 clauses, and each of them has at most 3 literals. So this one has 2 literals and the other one has 3. So since we have 3 SAT, then we have a structure which is bounded by 3. So we will represent every clause by this triangle. And in the triangle, we'll put a label which indicates the literal. So not x is replaced by not x in this thing, y, and so this not x or y or z, not z is this triangle. Okay. Similarly, this is not x or not y or z. Okay. So in this way, every clause contributes a triangle to my graph. So what does this triangle signify? This triangle signifies that if my independent set picks one of these things, say y, then it cannot pick the other two. Right? So what this is saying is it's going to make exactly one of these things. It's going to identify for me which of these literals is true in order to make this formula actually work out to be true. Right? So it's kind of giving me a witness from each clause. So in order for this to be a valid witness, if y is true here, then I cannot pick not y to be the witness for the next clause because y and not y contradicts each other. Right? So in addition to the triangle, I have these green edges saying that a variable and its complement will be connected by a green edge. Okay, so there should be some more green edges, perhaps connecting this y to that not y and this. Okay, so there should be, yeah. So this y to that not y. So every variable is connected to its complement to indicate that if one is there, the other cannot be there. So what the independence set is saying is it's trying to pick out a solution. It's trying to pick out a solution by looking at each clause, right, and saying that maybe I pick y here. If I pick y here, then I'm going to rule out these things. Okay, and maybe now I can pick y there. Then I have to pick something here. So maybe I pick x here. If I pick x here, I ruled out that not x. I have to rule out this not x. And now I'm in trouble because I don't have anything there. Okay, so maybe I could not have picked that x. So therefore, I go back and say that maybe I should pick this not x. This not x will rule out this x, will rule out this x, and will force me to keep this z. Okay. And now if I have an independent set of size 4, then I'm done. So I can say that the solution now I want is that x goes to false, y goes to true, and z goes to true. Right? So the existence of an independent set on this particular thing of size 4, which picks out one per clause. So notice that within a clause I can only pick one. So if I have 4 clauses, okay, and if I insist on the size of the independent set being the number of clauses, then I will definitely have got one witness per literal. And those witnesses have to be mutually consistent because I connect z and not z, x and not x everywhere by edges which rule out the same variable from being set true in one clause and false in another clause. Okay, so this independent set now picks out those literals which make my formula true. So if there is an independent set of size 4, then every clause can be made true in this set of 4 clauses, and therefore I have a solution to 3 SAT. And if there is no independent set of size 4, there is no solution. Right? So 3 SAT reduces to independent set, which is a bit more surprising than our reduction, as we said, from SAT to 3 SAT, which are both similar looking problems, or from independent set to vertex cover and backwards, which are very directly structurally related problems in the same type of graph. Right? So this is the surprising thing. It says Boolean satisfiability and vertex issues, independent vertices and graphs are connected. So we have shown that 3 SAT reduces 3 SAT. 3 SAT reduces independent set. Independent set and vertex cover are mutually reducible. Therefore, for instance, because I can now compose these reductions, SAT now reduces to vertex cover. Okay? And you can find in the literature such reductions for various other problems like traveling syndrome, integer linear programming, and so on. Now, in all these, it's important to remember that we are looking in this context of reductions where the pre-processing and post-processing step are polynomial time, because we want to say that there is no time lost in the reduction. Therefore, all the complexity is in the solution. If I have a simple solution for B, I have a simple solution for A when I reduce A to B. If I have a complex solution for A, then I cannot say that the solution reduction is what makes it complex. It is because the reduction is simple. It must be only the fact that the two problems are similar, that they are actually having the same complexity. So given this, when all these problems are inter-reducible, it means that all of them are equally hard. Now the famous theorem by Cook and Levin says that every problem in NP can be reduced to SAT. Okay, now this is a rather amazing theorem, because it says that if I take everything in NP, anything there I can reduce to SAT. Okay, so there is some reduction by taking an instance of that problem. I can convert it to an instance of SAT, solve the instance of SAT and go backwards. Okay, so we are definitely not going to try and prove this theorem here. It is enough to know that this proof is by encoding a suitably general model of computation. So the original proofs of Cook use Turing machines. You can take Boolean circuits or register machines, anything which is universal, anything which can compute every problem in NP, and then argue that the computation of that problem. So if something is in NP, there is an NP computation. There is a checking problem, a checking algorithm. So you can encode the behavior of that checking algorithm for that problem in SAT, and therefore it turns out that SAT is equivalent, or everything reduces to SAT. Okay. So this gives us a notion of completeness. Okay, so we say that SAT is complete because it belongs to NP and every problem in NP reduces to it. Okay, this is the definition of NP completeness. A problem is NP complete if, first of all, it has a checking algorithm. It belongs to NP, an efficient checking algorithm. And in addition, every problem in NP reduces to it via polynomial time reduction. Okay, so SAT by definition by the Cook-Levin theorem is NP complete because it belongs to NP, we know, and the Cook-Levin theorem establishes that every problem in NP reduces to it. But now we have seen that SAT itself reduces to 3 SAT. So every problem can be reduced to SAT, and then in a further polynomial step reduced to 3 SAT. So every problem now reduces to 3 SAT. But 3 SAT is also NP. So 3 SAT is also NP complete. Okay? So this is a generic technology now. So you have some problem which is NP complete, and then I reduce it to my problem here, and that makes B also NP complete. Okay, because provided B is an NP. If it is not an NP, then it is something weaker called NP hard. Okay, it is at least as hard as every problem in NP, but may not be in NP itself. Okay, so NP hard says that it is every problem reduces to it, but you are not sure whether or not it belongs to NP. You don't have a checking algorithm for it. Okay, so there are a few problems like this for which the checking algorithm is not easy to describe, but you can certainly show a reduction. But otherwise, if you can do both, you can find a checking algorithm, and every problem you have found some problem which in NP, which NP complete problem which reduces to it, then it is also NP complete. So this brings us back to this question of whether or not P is equal to NP. Right? So many useful problems which are extremely important for day-to-day life, like scheduling, bin packing. So bin packing is basically now if I want to put various objects into a container in an optimum way, okay, or traveling salesman tours, okay, if you want to find optimal tours. All these are very important real-life problems which people would like to solve efficiently. The theory of NP completeness tells us that all of these problems are actually inter-reducible and therefore equivalent to each other. If I can solve one, I can solve them all. Now we have this experimental evidence that since these are important problems, a large number of smart people have been looking at these problems from even before the time that computer science was invented. Right? People have been looking at scheduling problems and bin packing problems for hundreds of years. Okay? Therefore, these problems, if they have not yet yielded an efficient solution, then it looks likely that there is no efficient solution. Therefore, from an empirical point of view, okay, purely from experimental evidence, it seems to strongly suggest that NP is different from P. But this is not a proof, unfortunately. Mathematically, one has to argue that NP is different from P by giving a proof saying that there is a reason why some NP complete problem can never be solved using a polynomial time algorithm. Okay, this is what is called a lower bound. Right? So you need to establish a lower bound for some NP-complete problem. Okay, and this is very hard. This is proved very challenging. NP-completeness was first identified by Cook and Levin in the early 1970s. So it is now more than 40 years since the theory of NP-completeness itself was invented. And a lot of people have looked at this problem and nobody has yet found a direct way of doing this. Right? So a formal proof is elusive and it's worth $1 million because there is a prize given by the Clay Math Institute. So this is one of the celebrated open problems in mathematics for which the Clay Institute has awarded a large prize. So if somebody does prove that this is indeed not the case, then there is a large prize at stake. Okay? So with this, it seems an appropriate place to end this course. So I thank you all for listening.